Electricity and Climate Change, presented by the Stowe Electric Department in partnership with the Vermont Energy Education Program. Electricity drives our world. From home to school to work, we use electricity in almost all we do. But have you ever wondered where that electricity comes from? And have you ever thought about the results of all that energy production and use? Take some time now to write down or discuss where you think electricity comes from. First, let's take a look at how power flows around our world. Power originates at generating stations, which use the heat from burning oil, coal, and gas and nuclear reactions to produce electricity. Renewable forms of power generation include solar, wind, and water, also known as hydro. Electricity travels over power lines in order to reach your home. These lines may be located overhead on power poles or buried underground. Have you ever noticed all of the power lines in your town? The next time you travel around your community, see if you can identify the electrical equipment and power lines used to serve you and your neighbors. But make sure to stay safe and keep a distance, as dangerous high-voltage electricity is flowing through these devices. Outside, and occasionally inside, all homes, schools, and businesses, there are electric meters that record power usage. From the meter, wires run inside walls, floors, and ceilings that carry electricity to all outlets, switches, and appliances. When you switch on a light, turn on a dryer, use a toaster, or charge a phone, the electricity from the generating station finally reaches its destination. Now take some time to write down or discuss how you use electricity each day. We now know how electricity gets to us, but how is power really made? Let's start with a model of power generation using oil. First, wells are drilled deep below the Earth's surface to tap into oil deposits. After the oil is pumped to the Earth's surface and processed, it is burned to generate heat. This heat is applied to water to produce steam. The steam turns a turbine, which turns a generator. The generator is a device that is made of copper wire wound tightly around a metal core and mounted to spin inside an array of magnets. This action creates an electric field that produces current and provides electricity. Through this process, burning oil generates carbon emissions that are released into our atmosphere in the smoke you see coming from the smokestack of a power plant. There is a similar effect when gas or coal is burned to produce electricity. This carbon dioxide, also known as one of several greenhouse gases produced from the burning of fuels for energy, is the most significant contributor to the overall warming of the Earth. Greenhouse gases absorb energy, slowing or preventing the loss of heat from the Earth to space. These gases act like a blanket, making Earth warmer than it would otherwise be and throwing off the energy balance of the planet. This is known as the greenhouse effect. The sun warms the Earth. Some of this heat is reflected back out to space, and some is absorbed by the Earth and re-radiated as heat within our atmosphere. The correct balance of gases in our atmosphere allows for our climate to stay at an equilibrium. When greenhouse gases increase in our atmosphere, more heat is trapped, which results in an overall warming of our planet. Since the start of the Industrial Revolution, when world communities started burning more fuels to create energy for transportation, manufacturing, and energy production, we have seen an increased impact on the Earth from this greenhouse effect. the United States is now one of the largest contributors of greenhouse gases to the Earth's atmosphere. When you add up the percentages of all of the energy consumed in the United States in 2019 that was from non-renewable resources, it results in a total of 89% that was created using non-renewable forms of energy production. But how much does this really represent as we think about what was released into the atmosphere? According to the Environmental Protection Agency, also known as the EPA, between 1990 and 2018, the United States released between 6 and 8 billion metric tons of greenhouse gases into the atmosphere every year. How do we truly understand that the numbers are in fact in the billions? We look at the y-axis of the chart and see that it indicates in millions of metric tons. Thus, we must multiply the numbers on the y-axis by 1 million. When you multiply 1,000 times 1 million, you get 1 billion. Thus, the line on the chart is wavering between 6 and 8 billion tons of emissions each year. The EPA has also calculated how much the production of electricity in the United States contributes to the overall amount of greenhouse gases released to the Earth's atmosphere. As you can see by this chart, electricity represented 27% of all emissions in the United States in 2018. So how much does this mean in total metric tons of emissions? Let's have you do the math. According to the two charts, the United States released 6.7 billion tons of greenhouse gases in 2018. And by looking at the chart on the right, we see that 27% of all emissions are due to electricity generation. How many metric tons were due to electricity generation in 2018? Pause and take a few moments to calculate the answer. Now, let's check your answer. If you multiplied 6.7 billion metric tons by 27%, then you should have a result of 1.809 billion metric tons of greenhouse gases released into our atmosphere due to the burning of fuels to generate electricity. Now that we know what the United States is contributing to greenhouse gas emissions, let's calculate an estimate for all countries on Earth. The United States represented approximately 13% of all greenhouse gas emissions released across the globe. If the U.S. emitted 6.7 billion metric tons of greenhouse gases in 2018, and the U.S. represents 13% of global emissions, what is the total amount of greenhouse gases emitted by all countries of the world? Pause and take a few moments to calculate the answer. Now let's check your answer. 6.7 billion metric tons represents 13% of the total world emissions. Divide 6.7 billion by 13% and multiply by 100% to get the correct answer of 51.5 billion tons. This is a massive amount on a yearly basis, and the totals have grown significantly to current levels over just the past 100 years. To demonstrate this, NASA created a graph to show global carbon dioxide levels over 800,000 years. Over millennia, atmospheric carbon dioxide has never risen above 300 parts per million until modern times. Not only have we surpassed that number, but levels are more than twice what they were at their most recent lowest level. What is the result of this significant rise in greenhouse gases? Atmospheric temperature change due to the greenhouse effect. Let's look at a demonstration. As you can see from this NASA Scientific Visualization Studio progression, between 1880 and 2019, global temperatures have risen significantly. The scientific data indicates that the average global surface temperature rose by more than 2 degrees during this period. According to the National Oceanic and Atmospheric Administration, the Earth has not seen average temperatures at this level in over 3 million years. These higher temperatures are leading to climate change. We are already starting to see the effects in the world around us. Glaciers at and near the poles are melting. Droughts are lasting longer in some regions, while other areas of the world are experiencing persistent flooding. And the frequency and severity of wildfires and storms are on the rise. From this, we see that this is a big challenge to tackle. Where do we even start to change the cycle? First, let's start with transitioning the creation of energy with fossil fuels to generating more power with renewable energy sources. Renewable energy sources are those that do not run out because of natural replacement, and most have the added benefit of not releasing greenhouse gases into our atmosphere. The most widely used renewable energy sources include biomass, hydropower, wind, solar, and geothermal. In the United States, the sources of electricity generation are slowly shifting. In 2019, 11% of all sources of power for electricity were renewable, with this percentage growing each year. In the state of Vermont, however, the shift has happened more naturally and rapidly, with 99.9% of the sources of generation for electricity being renewable, which is a larger share than in any other state. Because of this and the state's small population, Vermont has the lowest carbon dioxide emissions in the United States at just 6 million metric tons annually, or less than 0.1% of total U.S. emissions. In Vermont, the top 3 renewables that do not contribute directly to greenhouse gas emissions are hydro, wind, and solar. Let's start with the most generated form of renewable energy in Vermont and see how it works. Hydropower is generated from the flow of water. Hydro generating stations are built along fast-flowing water sources, like rivers and waterfalls, or at dams that store water above the dam and then allow water to flow to a lower elevation. In the hydropower generation model, the flow of water hits blades that are part of a turbine, which then turns a generator that creates electricity. This form of electricity generation is considered renewable because rivers flow continuously with water sourced from rain, springs, and snow and ice melt. Let's see how we can generate electricity from the flow of water. For the demonstration, we will be using this generator, shown at 2 different angles. It is comprised of coiled copper wire and magnets, which will generate an electrical current as the mechanism spins around its axis. This current will allow us to power small devices, which will be connected with wires to the generator terminals. Our generator will now be connected to additional devices for our demonstration. As you can see, a water wheel has been added on the left as our turbine, also known as an impeller. And a voltmeter will show us if electricity is created. The voltmeter is set on the 5-volt scale, so we will read the numbers below the diodes or lights on the meter. Now let's generate electricity. As a flow of water is applied to the turbine, we can see that a current is flowing and we are able to achieve 2.25 volts of electricity. As the water speeds up, the voltage increases, and as it slows down, voltage decreases. If we scaled this model up to handle the flow of water from a fast-flowing river or high-powered dam, then we could see how higher voltages could be generated and the resulting power delivered to our homes. Wind is the flow of air that naturally occurs within our atmosphere. Wind turbines capture the power of this airflow to turn generators and produce electricity. Because of its natural reoccurring flow that does not create emissions when used to generate power, wind is considered a renewable resource. In the wind generation model, wind hits blades that are part of a turbine, which then turns a generator, that creates electricity. In this experiment, we will see how wind is captured to generate electricity, and you will participate in analyzing the results. Again, we have the voltmeter attached, but this time it is set on the 10-volt scale, so we will use the numbers above the diodes or lights to read the results. A wind blade turbine will turn the generator, and a fan will be used to generate our wind. During this experiment, the wind blade angles will be changed to see how the angle affects the total voltage generated. As each angle is tested, you should record each voltage reading in a simple chart with 2 columns labeled angle and voltage. We will be testing starting at 90 degrees down to a 0-degree blade angle in 10-degree increments. Let's watch. Be sure to record the voltage at each angle of the wind blades. Now let's begin, starting at 90 degrees. $80 degrees. $70 degrees. $60 degrees. $50 degrees. $40 degrees. $30 degrees. $20 degrees. $10 degrees. $0 degrees. Take a look at your chart. According to the voltages you recorded, what is the most optimal angle for the wind blades? Now pause and research or discuss the following 2 questions. Do you think the optimal angle would change if the wind was coming from a different direction? And do you think the location or height of a wind turbine makes a difference in the amount of electricity generated? Solar power is generated through the use of photovoltaics, which are the panels you see on the roofs of houses or in yards or fields along roadways. A large number of panels located and grouped together is known as a solar farm. Photovoltaics directly convert light into electricity using semiconducting materials. These materials exhibit a property known as the photoelectric effect that causes them to absorb photons of light and release electrons. When these electrons are captured and directed through conductive wire, an electric current is created and electricity is generated. To summarize, in the solar generation model, light from the sun reaches photovoltaic panels, which convert photons from the light to two electrons. The electrons naturally migrate to the front surface of the panels and create a voltage potential that is used to generate electricity. Now let's look at a demonstration of this technology. We will use a digital voltmeter set to record up to 20 volts and two photovoltaic panels, all connected together with conductive wire to form a circuit. Finally, we have a powerful light so that we can see the effects of differing light levels on the voltage of the circuit. Before we begin the demonstration, we are seeing between 3.1 and 3.2 volts from background light in the room. As the dimmer switch for the room light is increased, we see the voltage of the circuit rise to 9.7 volts. When the more powerful light is turned on and is focused directly on the photovoltaic panels, we see the voltage jump even higher. The maximum stabilized voltage we have achieved with all light sources in the room is 17.25 volts. As the light sources are turned off or dimmed, we see the voltage level decrease to its starting level with just background light. This shows us that even on cloudy days, we can still generate electricity, just at different levels than on bright sunny days. Now that we have looked in depth at three forms of renewable energy, let's see what other options we have for reducing greenhouse gas emissions. Developing efficiencies in the energy we use is another way we can reduce greenhouse gas emissions. Energy efficiency is the ratio of the useful energy out of a system to the energy supplied to the system. Energy efficiency equals energy output divided by energy input times 100. For example, we can calculate the efficiency of a solar array that produces 500 kilowatts of electricity using 2,600 kilowatts of sunlight. Energy efficiency equals 500 kilowatts divided by 2,600 kilowatts times 100 equals 19.2%. In order to be most efficient, we want the energy output to be as close to the energy input as possible and have little wasted energy. In other words, we want to get as close to an efficiency of 100% as we can. However, achieving 100% efficiency with power and energy systems is impossible, given that energy is often lost within the system because of the effects of phenomena such as gravity, friction, and resistance. Over time, as science and technology have improved, energy efficiency has also improved in all of the following areas: energy generation, building design, heating and cooling, weatherization, lighting, appliances, and manufacturing systems. Because of these improvements, we have been able to use less energy to perform the same work or even more work as with older, less efficient systems. By using energy efficiently, we can ultimately bring our energy usage down, which helps to decrease the overall amount of greenhouse gases emitted to the atmosphere each year. The final way we can reduce our reliance on burning fuels that contribute to climate change is to conserve. Conserving energy requires us to make changes in our lifestyles and habits, but if we all make a number of little changes every day, we can significantly reduce greenhouse gas emissions. In order to conserve electricity around your home and when you are in your school or office, turn off lights when leaving a room or install motion sensors to turn off lights automatically. Use natural light instead of electric light. Use power strips with on-off switches and turn off when not using. Turn off televisions, game systems, computers, and any other personal electronics when not in use. Remove electronics from chargers when fully charged. Unplug appliances when not in use. Use the air dry cycle on the dishwasher. Do not open the refrigerator often and do not stand with the refrigerator or freezer door open. Clothing washers and dryers consume a significant amount of electricity in our homes. In order to conserve, rewear clothing before washing if it's not dirty. Hang bath and hand towels to dry and reuse them. Wash only full loads of laundry. And hang your laundry to dry. Heating and cooling systems are also big consumers of energy. You can conserve by wearing more layers and turning the heat down in the winter. Turning cooling and fans off in rooms you are not using in the summer. Using outside air for ventilation, cooling, or warmth instead of turning on heating and cooling systems. And by closing doors and windows when heating and cooling systems are operating. Finally, water heating is something that we take for granted. We turn on a faucet and hot water flows. But the water heater is another big consumer of power in your home. In order to conserve, take shorter hot showers. Completely fill the dishwasher before running. And wash laundry in cooler water cycles. Pause and write down or discuss how you will save electricity every day. So to summarize, there are 3 key things that we can do to reduce the effects on climate change from the production of electricity. Convert more sources of power to renewable energy sources. Work to develop ways to make our systems that use electricity more efficient. And conserve electricity in our everyday lives. Please participate as we all work together to reduce greenhouse gas emissions into Earth's atmosphere due to our electricity use. Thank you for listening, and here's to a cleaner world. Remember to complete an online workshop form after watching this presentation. Electricity and Climate Change, presented by the Stowe Electric Department, in partnership with the Vermont Energy Education Program.